this is just this time was supposed to be where we just chat among grad students. It's very informal, so feel free to, not take it too seriously, a little bit seriously. So it's just gonna be, did we say 2 minutes or 1 minute?
2 minutes.
2 minutes, and then yeah, and then a question, one question or two for each person. We only have 11 people, and we have until 3. And then after that, there will be a discussion. I don't know about what, but that's what that's what the schedule says. So looking forward to that. Anything else?
Yeah, I think it's a chance for people to introduce themselves and maybe the dynamic students afterwards. What everyone works on. Yeah.
Should we go? Yeah. All right.
Yeah.
So the first person is Olivia McCauley from Bryn Mawr College. Oh, hey, Olivia. And yeah, we're not gonna time you.
No, it'll be quick because you literally just saw my talk. Okay, so I'm gonna just say again the basic idea of my project. So is that as you're growing the bar in the galaxy, you have this Lagrange point called L5, which I denote in pink. Oh, actually, you can kind of see it. Okay. And this mixture of this bar growth and Lagrange point could possibly be why we currently see it at near the solar circle, so about 8 kiloparsec. Okay, that's pretty much it, because I literally said everything else earlier. So I'm more interested in having conversation and discussion.
I might be totally blanking out right now, and so I'm sorry if you've said this. Why do we think that NGC 6791 has migrated in the first place? Like, why can't it just have been where it's always been?
Yeah, okay. So the chemistry of this cluster is very metal rich and it's very old. And so if you remember the third slide I showed, it was like the Landon graph of it was like the black and it had the different colors and all the colors were the galaxies, but then the purple color was NGC 6791. So that's a very unusual cluster. Like, why is it over there? It should kind of, you would expect it to be with the other clusters. So the idea is that based on the chemistry, it was born in the bulge and somehow it got to its current position because of the chemistry. So it's kind of like, let's follow the trail of why that is.
Yeah, so you just heard me talk not too long ago. So it's arithmetic, right? You guys all know this. The first thing plus the second thing gives you the third thing. And there you are. That's a lightning talk.
How much money would you be willing to bet on this?
Good question.
How much of your advisor?
I think.
From your advisor's line.
Yeah, I think the one Gaia sausage picture is not the full extent of what's actually going on in the halo, but I don't know if it's two things. It could be 1,000, right? But I think it's definitely not one. And either that or we're dramatically misunderstanding whatever this weird substructure is. So if it's not two things, it has to be one very young thing, which is still really weird because everyone thinks the Gaia sausage is super old.
Not exactly what I'm hearing, no.
No. Now I am. So yeah, the funny thing is, I don't know if any of you know who Vasily Belakrov is. He works at Cambridge, and he was one of the people to originally identify the sausage, or his group was. And the apocryphal story goes that he had that velocity plot, and he was talking to Adrian Price Whalen, among other people, and he said, you have this sausage, and then you have the meatball. And Adrian just was like, Vasily, you can't call it the meatball. So a little bit of history with this thing and people that you know.
Thank you.
Oh, you just heard from me. That's a stream. It fell apart, but there are two parts to it. You already heard me talk about it. Doesn't matter. The other work I do is fuzzy dark matter. I simulate fuzzy dark matter in efficient ways, in inefficient ways, not in inefficient ways. So typically fuzzy dark matter needs a cluster with a lot of computing time to run a simulation. But we've got a little trick, and you can run it on your computer. If anybody wants fuzzy dark matter on your laptop, talk to me. I can figure something out for you. Yeah. Oh my gosh, I have to call people. Very stressful. Go.
You first. Okay. What are you doing with the simulating of the fuzzy dark matter? Are you simulating like subhalo development or?
That's one thing we can simulate, and we're actually thinking of it. Generally, fuzzy dark matter is hard to simulate because you're dealing with a quantum mechanical being, which means you always have to resolve down to the Broglie wavelength. And the bigger, more massive the halo, smaller the Broglie wavelength. So if you want to simulate the Milky Way, you actually can't. What we're doing is we're solving for a stable halo, which means we can write out analytically what each of the eigenmodes look like. Superpose them, and that's actually much more efficient than solving the Schrödinger-Poisson equation on a cell by cell level. And we can basically resolve to any level we want because we just know the analytical shape of the wave. So basically, this gives us a good approximation of what things look like. It's hard to have things interact with it because we're assuming a stable potential. But if we're looking at small, like test particle-like things, if you want to put a stream in here, or if you want to look at what this does to, what is the signature for lensing? That is made of fuzzy dark matter. This is great. And
yeah, kind of answered my question, but yeah, I just wanted to ask that: are you solving the Schrödinger-Poisson equation to do this, or the fluid equation?
We are solving the Schrödinger-Poisson equation to calculate. So we are assuming a time-independent solution. We're basically assuming that, of course, all of the structure here is time-dependent, but we're assuming that the global shape of the potential is time-dependent. Basically,
how
things
do you
average.
get that potential form? Is it caused by the,
Yeah, so it is the potential is sourced by the density. It's self-consistent in the sense that the potential source is the density and is in turn the potential creates the eigenmodes, which in turn create the density, which sources the same potential. So we iterate a few times to get self-consistent.
So this is very good symmetric.
In this case, yes. It can certainly be done for non-spherically symmetric, but it's a little bit harder to solve the equation. Good question. I don't like to pick favorites because I'm not a betting man. I think it's very pretty. I don't necessarily think it's the most reliable. How about that? But yeah.
Strawberry.
Is it fast enough that you could feasibly have an embodied state of interacting with each other at each snapshot?
I can decompose those. So basically, I could say if we're assuming that those halos are, at each point you can like center on each halo and say each of those halos is a superposition of many, many, many eigenmodes. I can decompose both of the halos and say what's going on in each of the halos in terms of the interaction between the eigenmodes. I certainly cannot put one of these and put another one of these next to each other and evolve them kind of self-consistently, because again, this is assuming that this halo in itself is stable. So that's one of the areas we're looking
Hello. I just talked a few minutes ago. I'm Chris, graduate student at Columbia. And so I already talked to you before about this research I've been doing with the influence of Sagittarius and its various disruptions of the disk and how this could be responsible for radial migration. And just like how I showed, oh yeah, those are different. Okay, I'm just making sure those weren't the same. That shows you how good it is. So you can compare what you predict for the impulse approximation versus what you actually see in the simulation, and you see that just modeling this encounter is a very simple thing. Sagittarius appears, it applies a torque, and then it vanishes. It does pretty well at reproducing the global effect on the disk. But the other work I do, since I have much broader interests in dynamics, I also have an interest in galaxy formation. And so from the other work I've been doing, there's this sort of central tension in a lot of these like large-scale cosmological simulations between the necessity for very efficient feedback. And by that, I mean that you have to dramatically reduce the amount of baryons in galaxies by the present day, or else you get these very bloated, like overly massive galaxies. And so the primary solution to this is including some feedback, like from supernova or from AGN, which sort of launch mass out of your galaxy. But however, the solution that we want to try is, rather than having these winds directly injecting mass in the systems, they inject energy into the circumgalactic medium, which is sort of the gaseous halo that surrounds the galaxy. And so when this happens, these winds, when they inject the energy into the CGM, matter that sort of inflates the CGM, and then a fraction of the CGM becomes unbounded beyond the velar radius, and so that matter escapes the baryon system. And so this is more of what's referred to as preventative feedback, because rather than injecting matter directly out of the disk, you're preventing matter from ever getting there in the first place. And so, and this is the stellar mass, the halo mass function versus the stellar mass function, and it shows that varying the energy loading of the winds has quite a profound effect on the derived relation. Question?
These two feedback mechanisms are very different time scales. How do you, what's the improvement
Mm-hmm. Right. So the timescales is something that's, I think, very much still on the frontier. Like, it's very recently that I think there's been a more of an emphasis on thinking about preventative ways of feedback rather than ejective feedback. So the ejective feedback sort of happens almost immediately, because like you have these massive stars that are radiating so much energy that also contributes to feedback, but also when they die in supernovae, which happens quite quickly if they're very massive young stars, then the mass ejection happens like almost instantaneously like after that. While with the energy ejection, this is definitely like I think more of a extended process, because the energy has to escape to the CGM, has to inflate, and then slowly becomes unbounded, and sometimes the matter even comes back. So there's many knobs we have to tinker with at our disposal for preventative feedback model. Question?
From a phenomenological point of view, that completely makes sense. But I think one of the challenges in trying to understand these types of gas heating models is that how do you impart the energy, so much energy in the gas in the first place? And because photons very easily escape, even in case of ATM feedback, and just that coupling of that energy with that gas is very difficult. So how do you physically have an intuition for why that much of energy should be deposited?
Okay. Wow, it's we're getting quite deep here. I like it. Yeah, so we can talk more about this later. That's due in large part because when I came here, I was prepared to talk about this and to talk about that for like 2 minutes. So it's definitely like quite complicated, and I think it'd be best if we talked more about this in private. And so I can do it more reading. But yeah, it's definitely an interesting question, and we can get back to that. I keep getting so close to this mic. I really should. I talk way too loud for this microphone. Clap. Okay. Okay.
So I am working with streams. So I was talking a little bit about streams in my presentation, but this is a little different. So the main goal of my work is to try to use stream as a tool to detect like stream and subhalo interactions. And by these interactions, like if you see any signatures along the stream, we would like to be able to model like the properties of the perturbers in order to constrain the dark matter, the underlying dark matter models. So fuzzy dark matter could be a potential dark matter model to use. But anyways, so the way that people have been tracking stream subhalo interactions is just by like doing impulse approximation in real space, like X, Y, and Z. But the streams in Phi2 simulation is just like very long and very convoluted. So it's like a headache. And there are like all kinds of substructures in the simulations with all kinds of masses and like orbits and stuff like that. So what I'm thinking now is just trying to develop kind of a framework to track the stream subhalo interactions completely in the angle space, action angle space. So the plot I show on the left is just like the one of the streams in frequency space. So as I just said in the presentation, it's just like a long thin line. But so what I think of an interaction is that once the object comes in, it will create some sort of like a discontinuity in the velocities first. And then after some time, there would be some discontinuity in like the density or like the positions that will show up later on. So in this case, in action angle space, I would expect some sort of discontinuities in action or discontinuity in frequencies to show up first before we see any discontinuities in the angle space. So yeah, because in frequency space is so easy, it's just like a one line, and we have like a line detection, so we can project some sort of like a distance along that best fit line and stuff like that. And we can do some sort of like using like the KD, the kernel density estimator, to estimate the density of the points along the line. And for this particular one, you can think of the KD score as like the log of the density. So on the right-hand side, I just show the KD score of the particles along this line in frequency space. And there is a drop in the middle that I circled there, which might be a signature of an interaction. But yeah, I just don't have time to look into it too much. But yeah. Any questions?
What
Yes.
what mass is this stream?
This one is just slightly, maybe like 5 times 10 to the 7 solar masses.
Is this like really a follow-up question? As you know, an observer who cares about stars less than like half solar mass, how do streams actually work in fire? Because each of your stars is like hundreds of solar masses, right?
Right. In fire, each star is like 5,000 solar masses at present day. So it's huge.
10 stars, like 12 stars.
So the streams that we are talking about is not like global cluster streams like the GD1, but we are talking about streams from dwarf galaxies, such as like Sagittarius, and those ones have mass around like 10 to the 8 and stuff like that. So each stream will have like thousands to like 10,000s of star particles to begin with. So yeah, I think the higher resolution of fire is still running, like the triple latte, which hopefully will be able to resolve streams from global clusters. But for now, the only way to produce stream from global clusters is just by particle injection into the simulation directly. Yes. Mm. Right, I think I saw that. Yeah. Yeah, I can, yeah, definitely look into that.
Yeah. So comment to the comment. I think that's also that kind of power spectrum analysis is very useful for lots and lots of interactions with smaller subhalos, but not like one big thing smashing through the stream.
It's repeated bombardment.
So like not like the, if the gap in GD1 is real and Adrian found a dark matter subhalo, not that kind of thing. But like lots of much smaller things kind of battering it consistently.
Right. Yeah, they're sensitive to different
Yeah,
matter
I'm not-
subhalo sizes too, right? So
Yeah.
if one is
That's all kind of folded
more
in.
common than the other, then you see that.
Right. Yeah, and also like some substructures that interact with the streams, they tend to have like common orbits. So some of them are likely to interact multiple times along different parts of the stream as well.
I had a question. Since this is the fire simulation, I suppose you have some kind of snapshots of each time step that form this gap. Is that true? Can you constrain anything about the?
Yeah, for sure. I haven't looked into the time evolution of this thing, but yeah, each snapshot between snapshot is like 200 mega year, 20 mega year,
100 gig a year.
20 mega year.
20 mega year, okay.
Yeah, between snapshots. Yes, Tomo. Right.
I would imagine that every now and then you should actually something happen at rational ratio of frequencies. I would imagine that's an artifact. Do you ever see that? Basically, that you've assumed a somewhat like mildly incorrect potential, and it creates a structure that isn't actually there. Do you ever see that in frequency space?
Yeah, I do see like weird features sometimes, especially with M12F, the one where there was like an LMC analog. So I'm not sure if the artifact in frequency space arises due to the incorrect potential, as in not modeling the snapshot with the LMC correctly, or whether it's real. Yeah, so I don't know how to tell. Yeah, I have to think more about that.
So obviously you already heard from me as well, but I'm Adri. I'm in the physics department at Princeton. And actually I'd consider myself to study particle phenomenology, so not really galactic dynamics, but my advisor told me I couldn't give a particle physics talk at Galactic Dynamics Symposium. But so, I hinted at this in my talk, so I'll just spend this minute talking a little bit more about the particle physics. But so, long story short, I showed this very complicated plot during my talk. And what's really important here is that, we created this neural network to predict line of sight velocities. And we kind of showed, when you look at the difference between the yellow dashed line, which are network's predictions, with the blue lines, which are the truth, that we're actually doing a really good job of capturing velocity correlations with our network. And something that I really want to do that I find interesting on the particle physics side is figure out, what's the implication for dark matter experiments. So we talked a little bit about this if you were at my table at lunch, so I'm just gonna kind of rehash that. But so in our direct detection experiments, you have some sort of dark matter particle that interacts with the nucleus, and then it produces this observable nuclear recoil that we can measure in our detectors. So you can actually, calculate the differential scattering rate. And what appears in this formula, which I don't have here, but you have all of your information that you have to input from your favorite dark matter field theory, and are you looking at spin-independent interactions, spin-dependent interactions? But something else that's in that formula is exactly the dark matter velocity distribution. So it's really important to know what the local dark matter velocity distribution is in the solar neighborhood. And as we heard about so many times during the presentations today about, the Gaia's Tosses Edgewise was this huge merger, about, was it like 13 giga years ago or something like that, that's left to be disputed. Yeah, okay, there we go. So it merged and it, disrupted our galaxy, and most of it's virialized in position space right now, but we can still see it in velocity space. And this paper that I just showed here, this might have been a sim or actual data here, but I think it's been done in both cases, and you can show in the light purple here is stars, and the dark purple is the dark matter, and you can actually show that for this very specific type of structure called tidal debris, that the light matter is actually, the velocity distribution will actually track that of the underlying dark matter. So the idea that I talked about was, if we can find more stars that belong to Gaia Enceladus, we can essentially do something like this and then map it all the way back to the dark matter velocity distribution. Yeah.
I had a question mostly about the neural network that you use.
Yeah.
Could you elaborate a little bit more about the choice that you made of separating uncertainty prediction versus the line of sight velocities?
Yeah.
Why didn't you convolve the data with its own uncertainty and then just do that? Then the second question would be, why that architecture? Is it just feed forward? Is there some convolutional layers, or just feed forward?
Yeah, so it's feed forward. And why didn't we? So there were definitely other options that we had for our neural network. There's something called a mixture density network, which essentially does the same thing that we're doing here, but it doesn't output two different predictions. Well, it does, you can output the uncertainty and also the line of sight velocity, but you're not doing it separately. The way we approached it was to have these two different halves of the network. And the motivation behind that was just, we had a structure that had been used in previous works. It didn't have two different outputs, but we knew what we wanted to output, which was the line of sight velocity. But we also knew that, specifically, I don't have the equation here, but if you're looking at, if you're looking into minimizing a weighted Gaussian log likelihood, you're going to have the second term that has some kind of sigma, some kind of uncertainty value in it. And we really wanted to see if that information was going to prove useful to us. And yeah, I think the best way to see that is in this plot, because I didn't talk at all about the white dashed lines in this plot, but that's actually just the network prediction without considering the uncertainty values. So, you can see the network is quite overconfident, is what we would call that, when you're just looking at the white dotted contours. And when you actually sample over the errors, you end up with something that really reproduces the truth distributions. And that's something we can do when we apply the network.
Have you looked at the cases where the network really fails and
Yeah, great question. So we did a bunch of testing, as I kind of mentioned to some people at lunch. We did essentially the way we found our network structure was a bunch of trial and error. And there are some really cool new techniques in the works about how to actually find network hyperparameters without having to do a full parameter space sweep. But essentially, we did a sweep, and there are definitely certain cases. For example, so we've trained on those 5D coordinates from Gaia that I mentioned, but if you, for example, only trained on like galactic positions XYZ, then the network fails. So there are certain things that, for example, the velocities that the network definitely needs if it's going to produce some kind of reasonable distributions. Yeah.
Are there like certain, like, obviously it's not to be right about every rate of velocity. Like when you match back to these predictions, like are there certain places where like, oh, like I started with really high program ratios, but
yeah, great question. So we did put some restrictions on our data set. So we're looking at stars with low parallax errors. We throw out stars with exceptionally high velocities. So that's like absolute value of the line of sight velocity in our mock is if it's greater than 550, we kind of threw that out because we saw that those were skewing the data set. In terms of regions of the sky where the network appears to be doing better, we did look into that a bit. It seems like, the way we can tell that is we can look at a map, we can plot these velocities and plot the uncertainties on a map of the sky, and then see, are there regions where the uncertainties are a lot lower or a lot higher? And I don't have that plot with me right now, but I think we decided that they weren't significant enough, the differences in different regions of the sky, to be worth considering, to be worth narrowing down, just because they were so similar. So we're not restricting our stars in any way on EDR3 except for the parallax error cut and the exceptionally high velocities. Yeah. Oh, sorry, in the middle. Yeah. I was just kind of
you're sweeping.
Yeah, I was just going this way.
Cool. So let me be greedy. I'm gonna ask two questions. One is like a grandma question. So, what's your favorite kind of dark matter?
Okay. Yeah, I don't know. I might have to default to I don't know if I have a favorite. I don't know. The WIMP looked pretty good for a while because light is supersymmetric particle, but who knows what's happening there with the supersymmetry and everything. But as of right now, I don't have a preference. I'm definitely willing to throw whatever field theory in the scattering rate equation and see what happens.
Cool. My other question is, what happens if you look at like the mock data generated in different potentials? So that was like kind of mentioned before, but not necessarily as like a test set. Like, could you just generate a test set of like an alternate universe in LQA and see how it does?
Yeah, I think that's a great idea. That's not something that and the person who asked the question during the talk talked to me after about this. So it's not actually something that we've done, but I think it's something that could be cool to do. Considering the preliminary results that we've had on EDR3 data, because so what we're not doing is we're not using the network that was trained on the mock and applying it to data. We're taking the network that we designed, we're training it on data, and then applying it to data. So I think it'd be a cool test to do, to train it in different potentials, but at least for right now, while we're just using Gaia data, it wasn't like at the forefront of our mind, but I think it would be really interesting to check that out. Might have implications for, like I mentioned before, I'd definitely be interested to see if the error bars change and what happens with that, because that might have implications for, can we find strings with smaller dispersions? Was there a question? Yeah, okay.
The stream was like down here. Yeah, exactly. He's mapped it.
I guess what is your opinion on the state of dark matter direct detection experiments?
Yeah, we had a little bit of. I'm not a dark matter experiment. I don't think I'm as cynical as other people though, because we saw some interesting results from Xenon 1T at the beginning of last summer, which maybe we discussed a bit, but there's always a question if the background is too high or the background's contributing to what we see as a peak in the data where we don't expect there to be a peak. But yeah, someone mentioned, maybe Tom mentioned at lunch that there's definitely some experiments are hitting limits, right? Where there's not like physically enough material that they need to see if there's a dark matter interaction. I don't know. I just think the scattering rates are so low that you're just like waiting to see things that might not happen. But I'm not a cynic in the sense that I don't think they're worthwhile. I think they are, especially, as long as we're making advancements in on the astro side that we can apply to the particle side. I think it's pretty cool. Yeah, and there are other like the looking for the relic neutrino background and doing other stuff like that.
The action experiments are pretty promising.
Yeah.
There's some tabletop experiments that you can do to detect PCD actions.
Are you from Yale? Okay.
Yeah.
Oh yeah. I knew that Yale has a lot of tabletop experiments.
Yeah, we just hired someone who came from Yale who's doing
someone at Princeton. They got a tabletop axion to
the basic guys. The basics.
I have a really quick question about something that's nagging me a lot is if we think dark matter is a particle, like for direct detection experiments, like why are we looking at galactic scale velocity distributions? Because we're observing from Earth, not the solar neighborhood. So even if we have the most perfect model of the solar neighborhood's dark matter velocity distribution, like who is to say the local, 1 meter square meter, velocity distribution is the same as parsec level velocity distribution?
I think you account for the motion of the Earth, right? That's something that we know pretty well. So you account for that in your model.
Yeah.
But that still says the question of why do we think the bulk motion of dark matter particles on the parsec level scales pertain to AU level scales? It's like saying, galaxies are moving in one direction, so all the stars in that galaxy are going to move in that direction.
Right. Yeah.
It's not the case.
Is it?
I mean, that
Is it?
it tells you about the type of dark matter.
I just but it's probably where I just don't know how we would right, like all of the evidence that we have for dark matter is it's indirect and it's on astrophysical scale. I guess we're just trying to keep narrowing down the region that we're looking at until we get something that's small enough that we can use our indirect evidence. Right? I mean, I feel like the way that we counter that, which is what you just said, is if you actually do get a signal in your dark matter detector that is not explained by any lithium background or any of these other excesses that we're considering, and then maybe work backwards from there and see. But I guess that's the solar region is kind of maybe the smallest scale that we're actually right. Our Milky Way is is our test set in our backyard. That's pretty much what we've got. We're trying to look on that.
The formula
is it the local average?
Yeah, you have to integrate it.
Density is probably an average. It's not like.
Yeah. So you do integrate over the wall.
The anthropomorphic principle is what I'm trying to bring back here.
Oh man.
Yeah, anthropomorphism doesn't matter.
Also, I feel like you've been talking for 10 minutes.
Oh, no, I don't know. We started talking about
Hi, is it too loud? I'm Dhrubo, I'm from Yale. So like Tomar, I also work on fuzzy dark matter, but unlike him, I can't do it on my laptop. That's because it's a self-consistent simulation. And so as Tomar was saying in his talk, that he assumes that the average potential is stationary. And making that assumption, he finds eigenfunctions and does summation of the eigenfunctions to get how the density profile evolves. But I don't make that assumption, so I run self-consistent simulations, and so I have to use supercomputers. And what I'm showing here is what happens to a test particle, which you place. So it's supposed to be a nuclear object. You can think of it as a nuclear star cluster or a black hole, which is initially at the center of the soliton. We place it at rest at the center of the soliton, and then what happens with time? So we find that it starts moving out, And this has to do with three things. One is that the quasi-dark matter halos have this thing called a soliton, and then there are like quasi-particles or density fluctuations outside the soliton. And so the soliton sort of wobbles around, and that's because of its interaction with the quasi-particles. You can't see that here because this is centered on the soliton always. And then there is also the fact that the soliton oscillates. It has density oscillations. And so these are the two main mechanisms. And also because of the halo density fluctuations, we have potential fluctuations in the halo, and that start to kick the particle out. So basically, this is for a one halo, one boson mass. But once we are able to make predictions for different halos, different boson masses, we can sort of be able to use offsets of nuclear star clusters or supermassive black holes and use that to constrain the fuzzy dark matter particle mass. So that's the idea. And then I've also worked on ultra diffuse galaxies. And so this is, I looked at the evolution of the globular cluster system in the famous, you can call it famous or you can call it infamous, both. So it's the supposedly dark matter less or lacking dark matter galaxy, and this is 1052 DF2. At least we know that it has very little dark matter, even if no dark matter. And so we look at how the globular cluster systems, the typical or the speciality of this galaxy is that it has very massive globular clusters. And we look at how these globular clusters evolve over time, and basically whether the dynamics of the globular clusters is consistent with the mass of the galaxy. So basically, like there were some propositions that since these globular clusters are very massive, they should quickly sink to the center of the galaxy. And so it's not, so there was something wrong with the measurement. But what we found is that no, that's not the case. Even when the globular clusters are massive, they do sink in, but it takes a long time to sink in, first of all. And then the second thing is that when they start sinking in, the profile of the galaxy is a core profile. And because of that, there's something called core stalling, which is like if you have a core profile, then dynamical friction doesn't exist inside the core. And so they start stalling near the core. And also the fact that the globular clusters interact among each other, and that sort of helps to keep the globular clusters bind. And so there is no problem with like having a galaxy like this, which has little or no dark matter and has massive globular clusters. Thanks. Yeah.
How much core stalling do you need? So are you saying that you would need to have a core to do this, or?
Yes. So first of all, like okay. So to keep the globular clusters at the position that they are observed, you would need a very large core, right? But what we found is that, I mean, even if the globular clusters evolve, right? Even if you have a small core, at some point they will saturate. So there isn't any problem in the system evolving over a 10 gigayear timescale. It just means that when it formed, the globular cluster system formed in a slightly more extended. So we sort of estimated that, let's say, so we know that the age of the globular clusters are like 10 gigayears, and so the system had to be at least twice in size larger than what it is today because of this evolution. But yeah, if you want to keep the globular clusters at their present positions, then you would need a very large core. Right. Yeah. So Fornax basically is the same issue, that in Fornax also the globular clusters. So if Fornax had a cuspy halo, then people have found that globular clusters would sink in quickly, and then you would need a dark matter core to keep the globular clusters from sinking. But the difference here is that in the model that I make, I assume that the galaxy has no dark matter, because the observations of this galaxy are consistent with having no dark matter. And so this is basically the same effect, but with a baryonic core. So that's the difference with Fornax. Fornax is dark matter rich, yeah. There's no like with kinematic measurements, there is no scope for Fornax not having dark matter, but there is scope for this galaxy. Yeah. Well, so you can look at, say, op-centered, so you'd have to find star clusters which are not at the center. So so dwarf galaxies, there are of two kinds. Ones are nucleated dwarf galaxies, and then ones which are not nucleated. And so we would be looking for galaxies with op-centered nuclei, and we can make predictions from the model, like how far out they should be, and then for different boson masses, and then we can compare that with observations of op-centered nuclei or op-centered supermassive black holes. Both would work. Yeah.
So I don't know too much about the dark matter. So on the left there, what ends up adding energy to particle? Because I would expect that, it's not just one particle doing this, it's a lot of particles doing this. So all you're going to be.
Yeah, so the halo would lose energy over time and the particle would gain energy. I mean, yeah, there has to be energy conservation as a whole. So yeah, losing energy from your dark matter, and yeah. That's a good question. I'm not sure whether you could.
This kind of this favors
Well, yeah. So once we have predictions for different axion, this is for one halo, right? Yeah. So once we have predictions for different halo masses and different boson masses, then we can put constraints. Yeah. Thanks.
Hi, I'm Kostav. I'm from Yale, and I don't know what I'm doing here because I don't work on galactic dynamics. But I'm very interested in galactic dynamics. Well, I do use spherical Jeans equations, so I hope that counts. So instead of looking at kinematics of stars or stellar streams, I look at kinematics of satellite galaxies in the entire SDSS dataset below redshift of 0.2. And what I try to do is infer galaxy-halo connection, that is trying to estimate which type of galaxies are living in which mass of halos. Now that's traditionally has been done using clustering or galaxy-galaxy lensing, the two very well-proven methods of estimating halo mass. But this group knows better than anyone else that kinematics is another fantastic way to estimate halo mass, and it has been quite underused in the cosmology community. So what I do is try to estimate halo mass for all galaxies in the SDSS sample using satellite kinematics. Start with cosmology, which gives the information about halo mass function, that is the abundance of different mass of halos, their concentration parameters, etc. And with cosmology, I combine a model for galaxy halo connection, which is probability distribution of galaxy properties given halo properties. For example, it could be conditional luminosity function, which is just the connection between galaxy luminosity and halo mass. Given all that information, I can create a mock universe with halos and galaxies in them. And in that entire data set, containing close to 500,000 galaxies, I can pick out central and satellite galaxies and look at their line of sight velocity and projected separation of the satellite galaxy from the central. In cosmology, we do not have 6D phase space information. So that's all the phase space information we have, line of sight velocity and projected distribution, projected separation. Now that still is a phase space distribution of where each individual point represents a central satellite pair. In that case, I use spherical Jeans equation, not to individual systems, but to the entire population as a whole, statistically. Individual systems have 4 or 5 satellites at most. So you can't use spherical Jeans equation there, but you can do it in a statistical sense over the entire sample, trying to reproduce this phase space distribution. And if that phase space distribution is reproduced by tuning parameters in the galaxy-halo connection, you're basically inferring the galaxy-halo connection. So the results are multifaceted, but one of the most useful results is the connection between galaxy luminosity and their host halo mass. And that blue line is our result for SDSS. The paper is in preparation. And this just shows that it's in very good agreement with previous results, which are from different other techniques like clustering and lensing. So now we have turned satellite kinematics into a competitive probe for galaxy-halo connection at par with clustering and lensing. And all these different probes of galaxy-halo connection depend on cosmology in different ways. So we can use all of them together and demand that their inferred galaxy-halo connection must be self-consistent. That itself puts very tight constraints on cosmological parameters. So we are working on that, trying to infer cosmology by combining these different types of probes. Thank you. Yep. Okay, thank you. Thanks a lot.
You're welcome.
Means a lot. Yep.
Yeah, we should definitely talk because Eddie's coming up on my book.
Yeah.
And I was trying to wrap my head around how to use you've done it.
We're doing it, yeah.
So is the information mostly in like the sausage? I'm sorry. That's all.
The information, yes, is mostly in that sausage. But the main problem in this phase space distribution is that there are interlopers, which are galaxies which are not satellites, not satellites, that is, galaxies which are not inside the halo. They're pretty far away from the halo. We are just looking at the same line of sight. And those galaxies are infalling, so have the velocity profile very similar to that of satellites. So these infalling interlopers are a real pain. And this wing of that sausage is just using the interlopers that are, which are galaxies which are clearly interlopers. There are no satellites having 2,000 kilometers per second velocity. We are trying to use them, the information that's there, to weed out the interlopers from the sausage so that we can get the true signal that we are looking for.
And if you ever want more dimensions in your data set, I know a girl that might know how to do that. If you're on this talk, guys.
Yep. Yep.
What kind of precision do you need?
So currently I'm working with SDSS, which has a velocity precision of around 15 kilometers per second, which I think in cosmological terms is fantastic. So that really helps a lot. And the sample size of the entire galaxy set is below that certain redshift is close to 500,000, which really helps with the statistics because other than that, I mean, without the statistics of the large sample, there is no point in using spherical Jeans equation to try to figure out anything.
Similarly, if you have time, prime focus vector graph will get there. We're doing our best. Probably help you more.
So actually, I added it very late. Okay. Did you post it? I posted it but it was during the first one. Oh, maybe we can just it's good. Yeah. I am that annoying person. Well, I mostly want to show a video. I'm a problem child, unfortunately. I mean, if I can do it from my computer. Yeah. Also, after this,
Are the dynamics also so that everyone else knows what we do? Because I feel like it's not fair on this because the other students don't know what we do. They don't know what to talk to us about. Unless you don't want to talk to us. They haven't listened here all week. They only saw your talk. So you're the only one they know about. Well, some of them. Some of them have. Yeah.
Is it being driven from here?
No. I think at least when you see the guy.
Because there's a dongle here, yeah. Should I just?
Oh, you can just connect your.
Yeah.
Yeah, that didn't stop sharing though.
Yeah.
This is just me.
It connected to something.
What's actually connecting? Is this just a charger?
It has an HDMI cable too.
So okay, so let's go to the next page where we talk, and then once Elise comes back, you can give your stage.
No, I like the idea where I think we should go around and have.
Yeah. So,
Oh,
right.
There you go.
Yay, success.
Okay. Hello. My name is Gus. Well, my name is Angus, but I go by Gus. So I'm a grad student at the CFA. I run isolated simulations of disk galaxies. In particular, I run using this feedback model called Smuggle. So Smuggle is very similar to Fire, so you can sort of use them interchangeably in your mind. And what I'm mostly focused on is sort of having isolated simulations which we can analyze, but which are easier to understand than cosmological simulations, because cosmological simulations, like the Fire simulations, are very complicated. There's a lot going on, which has its sort of pros, but also has its cons. And so specifically what I've been working on is coming up with a setup for analyzing the bar and the bar evolution when you have a gas phase, when you have feedback, and so on. And so basically this movie that you're seeing here is where I've taken an isolated in-body simulation which forms a strong bar, which is consistent with the Milky Way's bar, and I've added the gas phase onto the left. And so this has only quite recently gotten to work, but you can see how the gas phase, after that initial sort of period where the sort of oddities of the initial conditions sort of phase out, you can see that it has sort of something of a realistic gas phase. And so basically what I'm working on is understanding the interaction between the bars and the gas, the interaction between the bar and the feedback, looking at things like the gas and the feedback at Lagrange points, and so on. One interesting thing that we found, which is a very preliminary result, is that it seems that the pattern speed, so this is a plot of the pattern speed In blue, if it's a plot of the pattern speed over time without gas, and so the pattern speed is an in-body simulation sort of runs or sort of slows down over time. What we found is that when you include the gas, that actually what happens is the pattern speed actually remains constant. So this is the gas is, as it's falling in as it, into the center of the galaxy, is being driven into the center of the galaxy by the bar. It's losing angular momentum, which means it's providing additional angular momentum to the bar. And so we don't really understand why the pattern speed remains constant. That might just be a numerical thing, but this is sort of one of the first things that we're looking at and sort of quantifying just how much does the bar speed up due to gas infall, how much gas do you need to keep the pattern speed up, and so on. So yeah, I'm very excited to sort of work on these simulations, but yeah.
So that's with gas plus everything else, stars, gas, everything.
Yeah, exactly.
So I would expect like from the dark matter you have done a friction, gas don't get lost.
Yeah, that's reasonable. Yeah, it could just be an accident that the way that we've set it up this way, it ended up being constant. And that if we sort of, for instance, added more gas, that the pattern speed would increase. And if we added less gas, it would decrease, but at a slower rate. So yeah, but that's something that we have to look into. Yeah. Tom?
Do you do star formation with your gas, or is it just isolated gas?
Yes, there is star formation. So and so like we see things that are consistent with observation. So like there's star formation out until about where the bar is, and then the bar doesn't show so well on the screen, but there are two gas lanes here which is actually where the gas is feeding into the central region. And so along those gas lanes, there's no star formation because the shear of the bar actually supports it against star formation. And in the central, there's a central high star formation. Yeah. Sorry, I don't know your name. Harry? Oh, I thought you said Virgo. Oh, okay. I've forgotten what smuggle actually stands for. I actually don't think it stands for anything. Stars and multi-phase gas and galaxies. Yeah. And then do I see bar buckling? No. And actually, I was talking with Tom and Jason about this yesterday. And the in-body only runs at low resolution. I did see bar buckling. And once you got past a certain resolution, there was no bar buckling. Yeah, it's not a conspiracy.
That it can be generated artificially in some, that it could also possibly be generated non-artificially by resolution.
I don't know. The gas does not seem to change it, but we only have the gas after the bar is formed. I should say that like this is not how the Milky Way bar formed. So you know, it did not form. Well, I don't know. It would be really interesting if it formed 1.5 gigayears ago out of a completely axisymmetric disk, but I think it's unlikely. So they're very similar. There are some like sort of technical differences. For one, fire runs on top of this hydrodynamics code called Gizmo, which is very similar to SPH, whereas Smuggle is built upon the moving mesh code of Repo, which is like this sort of moving Voronoi mesh hydro scheme, and that those two have different sort of
behaviors in certain regimes. I think probably the biggest difference is Smuggle is a little bit simpler in the sense that, like it's what Federico Marinacci did was sort of pare down a lot of the decisions that were made in Fire onto sort of like the core assumptions that can be used, and still get sort of like a realistic model. But I will say that Smuggle is a little bit less mature than Fire, so it's younger. It's not quite as tested. Yeah. Yeah, a lot of the gas stays in the galaxy. So there is sort of like, well, the way I've made this video is not super helpful, but there's like a sort of a formation of a Flamen flow that occurs in this galaxy, in these types of galaxies. But a lot of the gas is sort of staying in it. It's not, especially because this is like a Milky Way mass galaxy, so there's enough potential to hold on to the gas. So the feedback is not strong enough to sort of completely eject the gas from the galaxy.